2 years ago. So good morning everybody. I'm Marco Selvi of INFM Bologna, one of the organizers of this school. I'm very happy to see you here. I know that many of you had a long journey yesterday, and so I hope that everything was fine at the end and now we can start in a critical way. So I'm going to introduce Professor Marco Pallavicini, Vice President of INFN. By the way, he is also one of the lecturers. You will meet him later today, but right now he is going to welcome you as on behalf of INFN headquarters.
Thank you, Marco. So welcome everybody to this school. The INFN is the Italian Institute devoted to particle, nuclear, subparticle physics, and has a long tradition in underground physics because we own one of the largest labs, which is the Gran Sasso Lab, and many of you certainly know it. And of course, we have a large involvement and interest in this kind of physics, but we also have a large activity in training and growing the new generations on this topic. So I thank the Sezione di Bologna, the Bologna section of the INFN, for organizing this year this school that is at its third happening, and I think the previous one was in Cagliari, the other one was maybe online because of COVID, and another one in Gran Sasso. So here today we are in Bologna. I hope you will enjoy the lectures. There are high-level lecturers that will introduce you the topics in many respects. Thank you. Enjoy the lectures and have a nice week. Thank you.
Yeah, indeed, the school is organized by INFM Bologna. We are in Bertinoro, as you well know, and This is indeed a university center that has been set up here as a hospitality, culture, and innovation. This is the motto of this place. Now coming to the school, a general overview. This is basically the plan for this week. So we'll start mostly from phenomenology, dark matter and neutrinos, and then we go deeply into the experimental side with the various techniques. We will have also an important session on statistics with the hands-on part. You received all the instructions to profit fruitfully also from this part. And then you also will be an important part of the school. Today we will have this short introduction via the speed talk, and on Wednesday the outreach event. To conclude, tomorrow we have an outreach event in Italian. Marco Cirelli, the next speaker, and myself will give a speech intended for the general public. Of course, you are anyway our guest if you want. It's in Italian, so you are free to choose. And last day, the last evening, we have the social dinner on Thursday in a beautiful restaurant with a nice view over Romagna, which is the land of this place. So I think it's time to start. Question? Yes.
Is there going to be a group picture, and shall we all bring our t-shirts in on one of the days if there is going to be one?
So yes, indeed, we will have a group picture, and we'll inform you when we plan to have it in order that you can wear the t-shirt of the school. Okay, thanks. And for any needs, logistical needs, just get in touch with me and the other colleagues of the organization who are at the back of the room. Okay, so I think we can start with Professor Marco Cirelli from Sorbonne University in Paris, Phenomenology of dark matter.
Okay, so thank you very much, Marco. I'm organizing yet another Marco. It's the third one this morning. So my name is Marco Cirelli. I'm going to talk about dark matter from a phenomenological and introductory point of view. I work at Sorbonne University in France at the LPTHE, and I'm a senior researcher. So this is going to be quite introductory. It's intended as a smooth introduction to the school, where we're going to see much more advanced topics later. And essentially, I'm going to cover the evidences for the existence of dark matter, which are probably familiar to many of you. Look at the overview of the candidates from particle physics, but also from astrophysics, the mechanism of production of these candidates, and then in the second part tomorrow, or probably the last part of tomorrow, say, I'm going to cover indirect detection and in part searches at colliders if time allows. So this is something, these last two topics are something that you will not see in the sense that this school is more directed to direct detection. So if you want some material, you should have a look at, it's not working. You should have a look at, it's frozen, sorry.
You should have a look at this material here. So there are some historical reviews which are in white here. There are some more recent ones with a historical perspective, such as this one here, and an entire book by Stefano Profumo. And then if you want something more in depth, so there are these lectures of another summer school that I organized a few years ago, where you have about 20 different courses on dark matter. And this is an updated and extensive review that we just posted on the archive a few months ago, and it should contain everything you want to know on dark matter, at least everything I know, and I try to put my picks in that text. I'm going to put the slides on the indicator later, so you're welcome to take notes, or you have to look at them later. So, okay, so let me start with an introduction, which is a sort of cheat sheet, a sort of executive summary of anything that you need to know on dark matter. In the next 5 minutes, I will tell you essentially all we know and all the established facts, and what will follow in the rest of these lectures are just, say, hypotheses. So the first thing we know is that dark matter exists, and we know this because of this, and this. We're going to go over this in detail in the next in 5 minutes from now. So galactic rotation curves, weak lensing, especially at the level of clusters of galaxies, and the entire evolution of the universe, in particular the CMB and the formation of large-scale structures. These are the 3 main things that people quote, and that we will also go into later. Just notice one thing at this stage, that dark matter as an additional matter that we add on top of the matter we know, as we see, fixes the problems or explains the phenomenology at these very different scales. So here we are talking about the scale of a galaxy, which is about 20 kiloparsecs, I don't know, 30,000 light years, up to galaxy clusters, which are about 1 megaparsec or something less, and then the whole history of the universe, which is of course the biggest scale you can think of. Just including dark matter, adding dark matter on top of known physics explains these 3 things at very different scales. Next, we know that dark matter is a new and unknown corpuscle, where by corpuscle I mean something that has granularity like matter, which is why we call it matter, and we'll come back to that in a minute. And we know it's some sort of thing which is still new and unknown, in the sense that it cannot be described like any particle of the standard model. We have no candidates in the standard model for that. We could discuss that in detail. There are some proposals, but none of them work. So not some other particle can fulfill the role. And what do I mean by corpuscle? I mean, so I'm not using the word particle here, because I don't want to be directly into particle physics. I'm saying that dark matter is some sort of corpuscle, some matter body. And in cosmology, as we will see later, the definition of matter is something that dilutes as 1 over the volume, so 1 over the scale of the universe cube, when the universe expands. This is the basic definition of matter, something that behaves in the intuitive way of density goes down as 1 over the volume of the universe. Now we'll go back to that in a minute. Next, we know very well, so we don't know what dark matter is, but we know very well how much of it we have in the universe. It's about 26% of the total energy and matter density of the universe. And if you restrict only to matter, it's 84% of the total matter. This is usually encapsulated in this quantity here, which you call omega dark matter times h squared, which is measured, for instance, by the Planck mission very precisely at, say, 0.12 with a very small error. So we know very much how much dark matter there is, very well how much dark matter there is, yet we don't know what it is. So omega dark matter is the fraction of dark matter over the total density of energy and matter of the universe. And h is just the reduced Hubble square, which for our purpose is about 0.7. There's a whole discussion about how much exactly is h, what's the precise value of h, but for our purposes is 0.7. So if you multiply 0.7 squared by this, you obtain the 26%. I'm just restating this one. So next, we know that dark matter is a neutral particle, where I mean electrically neutral, so no electric charge, and that's also quite obvious, otherwise we wouldn't call it dark. So of course it means that dark in the sense that it doesn't interact with light, Okay, so it has no interactions with light. It actually be more than that. It has no interactions with, I mean, very feeble interactions with the rest of ordinary matter. Okay, just as an anecdote, people usually say dark is not the right word. We should say something like transparent, because something which is transparent is something that doesn't interact with light. So we should call all this transparent matter, but instead we stick with dark matter. Next, and this is also well known, so dark matter should be something cold, or at least not too warm. Where cold means essentially with little thermal agitation, little thermal energy. And that in particular at the time of the CMB formation, which is about 400,000 years after the Big Bang. What do I mean by cold? I mean that its momentum divided by its mass, it's much smaller than 1, especially at the time of CMB formation, so at that time in the very early universe, 380,000 years after the Big Bang. So I'm not saying that dark matter needs to be necessarily heavy, but if it's heavy, it means that typically this ratio will be much smaller than 1, and so you will have something cold. If you have a dark matter in the form of very light or light particles, then you need to ensure that the momentum with which they are produced is very small. So essentially they are produced at rest. Right? So you can have two cases, dark matter which is very heavy and so it's almost naturally cold, and dark matter which is light, but then it has to be produced at rest. Another comment, so if it's cold at the time of the CMB formation, which means, as I said, very early, then it will stay cold, in the sense that in the rest of the evolution of the universe expands, dilutes, and cools down, and so also dark matter will cool down and remain cold for the whole time. It will heat up a bit when collapsing into structures, forming halos, galaxies, and so on. We'll see a little bit of that later, but not enough to spoil this assumption. Okay, now let's move on. It has to be very feebly interacting, which with the word feebly, I mean something, I don't want to use weak, because weak is SU2 left of the standard model, so I'm just saying feebly to say something that interacts, not strongly, very feebly, with itself and with ordinary matter. Okay, so it's something, it's a substance made of corpuscles that interact very feebly with themselves and with the ordinary matter, such as atoms, baryons, and so on. Sometimes people they use the word collisionless, which means without collisions, of course. But then I don't like this because on the cosmological perspective, you can say collisionless. Basically, it's the same as saying very few. But then if you say collisionless, then the whole purpose of this school is lost in the sense that in direct detection, you have no collisions in xenon or the other experiments and so on. And also in all the other search experiments, including indirect detection, colliders, and so on. So let's about collisionless. It's something that we leave to the cosmologists, but as particle physicists, we use maybe feebly interrupt. Yet another comment. So what do I mean by feebly? Well, we'll go into that later, but let's say that it has to be weak in the sense of the weak interactions of the standard model, SU2 left, like neutrinos also interact weakly, or weaker than that. It can be another force that we haven't discovered yet, whose intensity is smaller than the weak interactions of the standard model. Of course, it can also be zero. So it can be also a kind of particle that doesn't interact at all, other than by gravity. And that is so really collisionless in sense. And that is not nice because then it will mean that we never discover it with our experiments. But let's say that it has to be weakly interacting or interacting with a force which is weaker than weak, which I define as a feeble in some way. Next, it has to be a particle which is stable, a corpuscle, so something, an object, which is stable, or at least very long-lived. So the age of the universe is about 10 to the 17 seconds. This corresponds to 14 billion years. And so the lifetime of dark matter has to be longer than this, much longer than this. Otherwise, the universe would be depleted of dark matter very quickly. So what I'm saying is that dark matter doesn't need to be necessarily stable, completely stable. It can be decaying, but decaying with a very, very long lifetime of the order of at least 10 to the 17 seconds. We'll see maybe later tomorrow that actually the bounds on the decay of dark matter, depending on the channels, on the candidates, are even higher than this, 10 to the 20, 10 to the 28 seconds, but at least it has to be longer lived than the age of the universe. And we're almost done. So the other thing that we think we know is that dark matter is produced in the early universe. This is for sure. So dark matter exists in the early universe and then up to today, as we will see later. And it's probably a relic, so something which has been produced in some way in the early universe. We will see some mechanisms later. And then it's left over. I mean, it has survived because of the fact that it's stable, produced at some point just after the Big Bang, and then stays on. Okay, I'm done. So we want to search for it by typically 3 methods, which are sketched here. So direct detection, which means that you scatter dark matter particle over a standard model particle, such as a nucleon underground, or, and you will discuss this in detail later in the school, or with indirect detection, which means that you annihilate the 2 dark matter particles and produce standard model particles. I think, for instance, as of photons, pairs of gammas, or a positron and an electron, typically in space, and then you want to detect them. We'll discuss this tomorrow. And the third classical way in which you want to discover dark matter or to search for dark matter is at colliders, where you do the opposite of this. So you collide particles you know, such as protons at the LHC in Geneva, and then you produce dark matter and how to detect the production results. Okay? So as far as I know, these are the established facts of dark matter, nothing more than this and nothing less than this. So this is what we think we know for sure. All the rest is up to our speculations, which is what I will go into the next hour or so. So another thing that you have seen for sure many times is this pie chart, which is here, which tells you how much the different substances of the universe contains. So you know that dark matter, sorry, matter in the sense of luminous matter, the one that forms stars and so on, and also photons and so on. Rayleigh photons, Rayleigh neutrinos, the Rayleigh photons is about 0.01, so 1% of the total content of the matter energy of the universe. Baryons, in terms of gas, planets, black holes, all that stuff, contributes 4%. So these are the usual omegas, which are defined as the density of a certain species X divided by the critical density, which is the total. Okay? And as I said, H is about 0.7. And then the rest, the other 2 components are the dark stuff, dark matter, as we said, 26%, and dark energy, which is 69%. So the thing which is interesting for us is that indeed dark matter is at the frontier, is at the intersection between particle physics and cosmology. So it's something that comes from cosmology, of course, and it is related to, probably the solution will be related to particle physics, so postulating the new particle. Now, before I go on yet with another basic point, does everybody has a clear idea of the difference between dark matter and dark energy? I hope so. Okay, so let me just say a couple of words on that because it's interesting. So it's actually a very good question because sometimes there are confusions and people tend to think that the 2 might be related. And as far as I know, no, it's absolutely non-trivial to relate the 2. These are 2 different substances, completely different, that we call dark in both cases just because of historical reasons, but they are completely different stuff. So the 2 main differences are that dark matter behaves like matter, and this I already said. So it's something that dilutes as the volume of the universe expands, and clusters gravitationally on small scales, meaning that the particles attract each other and form denser regions. So this is what matter does. So attracts each other and forms clusters. So if you want to express that in terms of the equation of state parameter omega in cosmology, which is defined as the pressure divided by the density of a certain substance, this for dark matter is equal to 0, which is what non-relativistic matter has in general. So dark matter is something that has an equation of state equal to 0, and so has these 2 properties above here, especially this one here. Dark energy instead is completely different. So it's a fluid, it's some sort of fluid which does not dilute, so it remains constant all over the place and in time, so spatially and in time. And as far as we know, does not cluster, so it's homogeneous everywhere in the universe. So expressing this in terms of the equation parameter tells you that omega, divided, which is pressure divided by density, is equal to -1, or at least close to -1. Recent measurements by the DESI telescope say that it might be a bit away from -1, but let's say close to -1. And if you solve the Friedmann-Walker equations in cosmology, a quantity which has omega equal to -1, let's just think about plugging it in here, tells you that the acceleration of the expansion of the acceleration of the universe, so the increasing velocity in the speed of expansion, is positive. So dark energy is something that drives the accelerated expansion of the universe, while dark matter does not. I hope that's completely obvious. Two completely different things. And if I go into the basics even a little bit more, maybe you have seen this many times. So how are the components of the universe evolving in time? If I do density over time, matter decreases as 1 over a cube, as we said, so as 1 over the volume. So in a log scale, matter decreases like this in time. Radiation decreases faster, as 1 over a4, because it expands, it dilutes, but it also redshifts, and so you get that radiation becomes, the density of energy in radiation becomes smaller, faster than the one of matter. And instead, the cosmological constant, as we said, is or the dark energy is something that remains constant. If it's fully constant, we call it cosmological constant, and its omega is equal to -1. If it's close to that, it might have a little bit of variations. So these things, as you see, in the universe, in the history of the universe, say Big Bang is here and today is here, have a very, very different density. So there are different epochs in the universe. Okay, so let me introduce also neutrinos, which are smart enough to behave as radiation first, and then behave like matter later. So neutrinos do have mass, but that mass is small. So in the early universe, they are similar to radiation, similar to photons. They are relativistic particles, and so they behave like radiation. And then at some point, we don't know exactly where, their mass starts to be important, and so they behave like matter. So if I put myself as, so there are two important moments, the matter dark energy equality, which is here, and the matter radiation equality, which is here at a certain point in the evolution of time of the universe. This is not important for us, it's very important for a course in cosmology. So if I put myself at today here, this is the same pie chart that I mentioned earlier. So today we have 26% of dark matter in the universe. If I put myself much earlier, say at the time of the CMB, more or less, the formation of the CMB, which is this number here, as I said already a couple of times, you see that dark matter was 63% of the total matter energy content of the universe. Because cosmological constant was completely subdominant, and radiation was also subdominant, and so on. So this is to say that dark matter is the dominant actor in the formation of the universe for a very long time, which is essentially all of this, until dark energy takes over, which is yesterday in cosmological times. So if you do the percentage of these fractional densities of this plot, this same plot converts into saying that up to this moment, the universe was composed at least 100% by radiation domination, in this epoch by matter domination, and it's essentially dark matter, and dark energy domination very late at about 10 giga-years of age of the universe. Okay, so this is actually the same plot, so this is the same graph as before. So at the time of formation of the CMB, we had a 63%. Okay, so I'm done with the general introduction. Now we go and discuss the proofs, the existence, the evidence for the existence of dark matter in cosmology. Any questions up to here or any comments? Yeah.
I think it's a very naive question, but
No.
how can we estimate the total density of the universe?
The total density of the, okay, that's,
So
it's not at all an easy question, it's not at all a naive question. So basically you do it with the CMB itself. So I'm not going to do that because I'm not such an expert and it requires a lot of time. But let's say the total density of the universe, so the critical density of the universe, determines the geometry of the universe, whether the universe is flat, open, or closed. And the latest measurements by Planck, from the CMB and also just before, tells us that it's flat, which corresponds to that amount of the total critical energy. So you can measure the critical energy coming from the CMB itself. Okay, so let's move on and let's discuss the three things I just introduced naively earlier. So galaxy location curves, clusters of galaxies, and so-called precision cosmology. So before I go into that, let me tell you that this is very intuitive, so you will understand immediately, and actually you probably already know, but it's not particularly important. At this stage in time, it's essentially an anecdote. That, I mean, the general public understands very easily, but it's not what's important for us. The thing which is important for us is precision cosmology, so CMB and structure formation. Although this is much more difficult to explain, so I will just sketch it just with cartoons and movies and pictures, but it will require like 3 hours only of this. Okay, so just let's go a little bit into these details and then not too much into this, but keep in mind that this is the important thing that gives us evidence on our matter. So galactic rotation curves. Well, essentially it means the following. We are talking about spiral galaxies such as Milky Way or Andromeda and 31, or this other one here. And what we are doing is plotting the speed of rotation of stars around the bulge of the galaxy. So galaxies, spiral galaxies, such as the Milky Way or M31, are composed of a central bulge, which is here, which contains a lot of matter, a lot of stars, and possibly a central black hole, and so on. And then the spiral arms that rotate around. Right? So these are typical spiral galaxies. So we can plot the speed of rotation. Let's look at this plot. We can plot the speed of rotation, tangential velocity, around the center of the galaxy, and we find these data points here. So this is something which is completely surprising, right? Because if you think of a galaxy as made of a central body that attracts, that produces the gravitational interaction, which is the bulge here, you would expect the speed of rotation to fall down according to the so-called Keplerian descent. So following this curve here. Meaning that the peripheral stars should turn around the center of the galaxy much more slowly than the stars located at the center of the galaxy. Let me show that in formula. You're certainly familiar with that. So I'm saying that I can write down a sort of centrifugal force for the stars at a certain location R, and subject to a certain speed of rotation V of C. That should be compensated, that should be equilibrated by a centripetal force given by simply Newton law. So M is the mass of the star, G Newton, the location of the star, and M of R is the mass contained, the total mass of the galaxy contained within a certain distance R. So these two should be equal simply by Newton law if the stars stay in orbit. That means also that the speed of rotation, if I turn around very simply this equation here, should go with G Newton M of R divided by R under square root. I'm just turning around very easily this equation here. So if the mass of the galaxy M of R is concentrated in the center, which is what we see, so most of the stars and most of the visible matter is concentrated in the center here. As soon as I go to large R, I can say that this M of R is a certain constant that doesn't change anymore, right? Gauss theorem. So what is contained in the center is what enters here. So a certain constant big M. And so I would expect V of C to go down as 1 over square root of 1. And this is Newton. I mean, this is Kepler or Newton if you want. So the speed of rotation goes down as what is expected in this, this curve, which is called the disk. That is not the case So VOC stays constant in the measurements in this galaxy here, in this galaxy here, and also in the Milky Way, right? It's a bit more complicated to derive to do the analysis because we are inside. So that means that we have to have a way to have a VOC constant as a function of radius. And in order to obtain that, if I want a VOC constant, I have to impose that M of R, which is yes, so I said already that. So the matter contained the integral of the density up to a certain radius R. This is just the integral of the density up to R. If I want a VOC to be constant, in two lines, you realize that you want this M of R to be going as R, and so you need rho to be going as 1 over R squared. So what I'm saying is that there is an additional quantity of matter, which is not just concentrated here in the center, but which is distributed in the whole galaxy with a density which is typically 1 over R squared. And this is dark matter. The additional matter that we add in the galaxy is dark matter. So we have to add a halo of dark particles of some way, halo of this substance here, distributed as 1 over R squared, that gives this extra contribution to VOC that keeps the data points consistent with a constant. And indeed, if I suppose that the galaxy contains a gas of non-interacting particles, it distributes naturally as 1 over R squared, so we are already pointing towards a possible solution of this. There is an extra halo, an extra gas of those particles, non-interacting particles, that distribute as 1 over R squared and produce this excess gravitational interaction that keeps the far distant stars linked, attached to the galaxy. Now, a little bit of a caveat. So this is correct. What I said is correct, but it's a bit oversimplified, and it's mostly a negative proof. So what I'm saying is that the visible matter, the matter contained in the center, with standard gravity, of course, so with Newton's law, cannot reproduce the observed non-rapidly falling rotation curves, and someone else is needed. Essentially, this is what I'm saying. Then, if you really want to go into the details, these are a bit more complex. So some curves are not exactly flat, so you don't get necessarily 1 over R squared, and there are some parameters that you have to tweak in each one of the galaxies, but say that overall the picture is correct.
Sorry?
Yeah.
So you mentioned Milky Way and Andromeda, and now I started wondering how distant can a galaxy be that we can resolve their rotation curve? Like how many galaxies do we actually observe? This is like
hundreds or thousands. So, yeah. So the most one of the most complete catalogs that I know of, it's called Spark for spiral like something, and it has I don't know, some hundreds of galaxies, and they actually select the best ones. So you can go up to 1,000 probably quite easily.
Do you know roughly the distance?
The distance of these?
Yeah, the most.
No, I'm not completely sure. You have to be rather close enough in the sense that otherwise you don't have the resolution to see inside the galaxy so much of the rotation, but it's not particularly. No, I mean, I know the ratios of some of them. It's 0.1, 0.11, something like this. So one would compute.
But roughly 1,000 things.
Yeah, between 100 and 1,000 are the cleanest ones. Okay, so yeah, pictorially what I'm saying is that there is this distribution of dark matter in the galaxy, and we will discuss that in much more detail later, so the way it is distributed. Good, so let's move on and move to the second topic, which is clusters of galaxies. So here I could do the same as the rotation curves, in the sense that I could see how so what is a cluster of galaxies? It's a group of galaxies that are gravitationally connected between, say, 100 and 1,000 galaxies, roughly speaking, that move around in the cosmos in sort of connected way. So I could do rotation curves, so the equivalent of rotation curves, meaning that I could look at how these galaxies move around the center of mass of the cluster, and determine whether I do need some extra matter to keep them gravitationally tied or not. And this is what has been done actually originally by Zwicky in the 30s, the first one who talked of dark matter, but this is just a repetition of what we did before. So instead, the thing which we do with clusters is mostly gravitational lenses. So looking at the existence of unseen matter through gravitational lenses. This one is the thing that everybody always shows. This is the bullet cluster. It's a picture of a collision of two clusters of galaxies that happened like 5 billion or 5 million years ago or so. So this is the movie that tells you what's going on. We had two clusters of galaxies, one is this, the other one is this, and they went through each other in a sort of collision about 5 million years ago. And we are looking now at the aftermath, so what is left there, and this is the picture that we are expecting. So you see the in the optical, so with the Hubble Space Telescope, you see the clusters. This is one and this is the other. You see a little bit of overdensity of galaxies. This is what is called the target, and this is what is called the bullet. So the bullet cluster went through the target cluster here. The clouds of gas that accompany the clusters, so gas like ordinary astrophysical gas, they slow down, and you can see them here. So this is the cloud that was associated with the bullet, and this is the cloud which was associated with the target. And through the collision, they slowed down and they stopped in the middle. Due to the friction between the clouds of gas, what happens is that these atoms have been excited, and so they are radiating in the X-rays in order to cool down. So actually, this is an image taken by the Chandra telescope, which is an X-ray gas superimposed to the image of the Hubble Space Telescope. And so you get that these are ordinary clouds of ordinary gas that are just cooling down, emitting in the X-rays. What's interesting in this system is that you have two other large concentrations of mass, which are located here, which have appeared in blue. And we see those thanks to gravitational lensing. So it means that looking at sources in the background, behind the system, we can look at the deformation of the image of galaxies or other sources located in the background. And this tells us that there is something acting as a lens, a gravitational lens, in between the line of sight from the distant source to the point of observation, which is our telescopes on Earth. Okay, so according to general relativity, photons are distorted by the presence of matter, and so what happens is that the image of galaxies in the background just get distorted, and we can infer how much matter there is in the line of sight and what is its distribution. So one comment, so this is done statistically, in the sense that, of course, we don't know what's the shape of the galaxy in the background, or the sources in the background, but statistically, over many different galaxies in the background down there, we can see whether there is a special alignment of these galaxies in some way that betrays the presence of the lens, and this is how we reconstruct the presence of this matter here and its distribution. And second comment is that, okay, so the computation shows that the amount of matter which is needed to create this deformation, so the amount of lensing which is needed, is much larger than the amount of matter contained in the galaxies here. So if I count the matter into these 100 galaxies contained in this cluster, I find a quantity which is very much insufficient to produce this lensing here. So I have to postulate that there is an extra quantity of matter here, which is dark matter. So that's, say, the second proof of existence of dark matter. And in a system like this, it's particularly evident because in a system like this one, the bullet cluster separates spatially the presence of ordinary matter, which is here, so gas, standard gas, or the stars, and the dark matter, which is here in the blue regions. So to produce the lensing here, you are forced to say that there is some extra matter that you don't see, which we call dark matter.
So can you go back to the
When?
yes, the yellow line?
Okay, that's just an illustration. Yeah.
No, I just was.
Okay, so this is just an illustration to say that the photons emitted from that galaxy in the background are deviated, are deformed, their trajectory is deformed, as always when photons go through, go by a cluster of mass, a density of mass. I mean, this is just general relativity. Imagine space-time is curved around the presence of this mass here, so the photon goes around, not in a straight line, but in a curved line. I mean, it thinks that it follows a straight line in geodesic, but the geodesic is curved. Yeah.
I assume you can see this in all different wavelengths from galaxies on the other side.
Yeah.
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 You've meant that whatever galaxy you want to use, you choose whatever it produces more of.
Yeah, so as I was saying, this is done in a statistical sense. So I'm just sort of intuitively giving the concept, but what people do, and I actually have a plot, not a plot, but an illustration later, okay, is that they look at the statistical deformation of the background. So very naively, imagine that in the background here, you have, I don't know, 1,000 galaxies distributed randomly, and they are oriented in different angles. Okay. Typically, a galaxy seen from a side is something which is an oval or something like this. So typically, you expect them to be oriented in random directions. If lensing occurs, you will have that statistically these galaxies will be all pointing towards the central direction, roughly speaking. And so you can define a statistical quantity that tells you how much these galaxies are oriented towards the center. The shape of this galaxy is towards the center, and this gives you a way of reconstructing how much dark matter there is and its distribution. Yeah, I have a plot later. Yeah.
Is the amount of mass, effective mass that you infer from this, the same as the amount of mass that you infer from the rotation curves?
It's very difficult to say in the sense that each system is different, and typically no, in the sense that in galaxies, well, it's so every system is different. So in galaxies, the ratio of dark matter over luminous matter, which is called sometimes the mass to light ratio, can go from a factor of a few, say 4 or 5, up to 100 for the very faint galaxies that have very few stars and a lot of dark matter, are very dominated by dark matter. So in clusters, the typical factors are around 20 to 50, something like this. Okay, and in cosmology in general, instead, the ratio is about 5, because as you said before, there is a 4% of matter and 26% of dark matter. So no, but every system is different. You have a lot of variation. Okay, so as I was saying, this is done statistically. It's done in many different systems. The bullet cluster is the best known of all of them. But there are many more. For instance, this one is called, how is it called? The ring of dark matter. Okay, so you see in false colors the lensing due to the presence of dark matter, and you're supposed to see that there is some sort of alignment of the background galaxies. And let me show you a result from a paper, which is pretty old right now, which is let's look at the right plot intuitively. So you see that looking at about how many 72 clusters, which are written here with crazy names, you see that you can reconstruct the isocurvature, the isodensity curves of the distribution of matter in the sense that was mentioned before. So let's say look at this cluster here, you say that dark matter is distributed according to these isodensity curves, which are depicted here, done in the naive way I said before. Okay, so lensing is also very powerful, tells us a lot about the existence of dark matter in the universe. But the most important thing is the third thing, which is precision cosmology. And by precision cosmology, I essentially mean the CMB, so the cosmic microwave background measure essentially now very precisely by the Planck satellite, and the distribution of large scale structures, so the position of galaxies in the universe. So I suppose you are familiar with these pictures here. So this one is the picture of the CMB with the hot spots and cold spots, which are little differences in temperature on top of the constant black body temperature of 2.7 Kelvin. And this is a cartography, actually this is a simulation that, let's say, corresponds to a cartography of the different galaxies in the universe. So each point here, each luminous point here is a galaxy, and they are distributed according to a certain non-random pattern, which is what is called sometimes the cosmic web. So sort of scaffolding produced in the universe where galaxies are located. So how do we do the analysis of these quantities here? We do essentially the Fourier transform and produce what are called the acoustic peaks of the CMB, which are here, or the power spectrum of matter in the universe, which is depicted here. So let me tell you just very briefly how these curves come out, and then I will tell you that they contain a necessary dark matter. So what we do, let's look, for instance, at this quantity here. So this is the distribution of galaxies in the sky, for instance, measured by the Slow and Digital Sky Survey or any other galactic survey. And what I do is that I look for the correlation function between the different points in this, the different locations in this map. So naively, what we should think of is that you take a given length, say here I have a certain ruler of, I don't know, 1 kiloparsec or 1 megaparsec or 2 megaparsec, and I put it on top of the map in all possible positions. The correlation function means that if often I find at one end and the other end of the ruler a galaxy, so a peak of the density, that means that there is a large correlation associated to that length. Okay. If instead I find often I find a galaxy on one side and a void on the other side, it means that the correlation is weak. So there is no correlation between associated to that length on top of all over this map. If I do the Fourier transform of the correlation function, what I get is the power spectrum. So something that has a shape such as this one here. So for instance, here I've taken, and also what I'm saying is that the power spectrum expresses how powerful, how strong, or how weak is the correlation function on the original map. So let's look at this length here, just as an example. This corresponds to 1 megaparsec. And if I do the power spectrum, and if I compute it, if I do compute the Fourier transform, I find that it corresponds about to this quantity here. So here the power is small, meaning that it's unlikely to find two galaxies separated by 1 megaparsec. If instead I take a bigger ruler, say, corresponding to a few megaparsecs, then the power spectrum is larger, meaning that it's more likely to find two galaxies separated by this distance here. Here I'm plotting the power spectrum as a function of the wave number, so it's a Fourier transform, so it's the inverse of the length, and so this is measured in 1 over megaparsecs. So smaller wave number means larger size, physical size of the imaginary ruler. So this is the power spectrum that I compute and I extract from a mass like this. If I compute, theoretically, the power spectrum that matter should have, the galaxy should have, in a model that includes dark matter, and a certain amount of dark matter, I get the black line, which is this one here, which corresponds exactly to, which fits exactly the data points which are here, given by the distribution of galaxies in the sky. Okay, so I need a cosmological model that includes dark matter to create this distribution of galaxies that fit what is seen in the galaxy surveys. If I put 0 dark matter, you will see what happens. I will not have any of this structure. And if I put a little bit more, a little bit less of dark matter, I will have this line that goes a little bit up or a little bit down, and so I will be able to determine the right amount. The right amount is 26%. You can do the same thing on the CMB. So the CMB, you have an overall back body temperature, which is 2.725 Kelvin. And as you know, you have some spots which are a bit hotter and some spots which are a bit colder by a tiny fraction of about 10 to the minus 5 on top of the total temperature. So you do, again, the Fourier transform of this thing here, and you get this line, which is the equivalent of this line on the map of the photons coming from the CMB. So now here, the distance is not a ruler, but it's something, since this is projected on the sky, what I'm considering is the angular opening, which is, yes, so under which angle I see the spots in the sky. And in particular, this it's the same argument that I did here, except that for angles. So for 1 degree of aperture, you are here, that you see this peak here. And if you instead go to wider angles, you would move on the left. And if you go to smaller angles, you would move on the right. So also from this, and actually much more precise than from this, if I include in my cosmological model the presence of dark matter, I get a black line that goes through the data. If I have no dark matter or fewer or larger amount of dark matter in my cosmological model, I will not go through the data. Let me show you how it works, naively how it comes out. So for instance, let's look at the CMB. If I put no dark matter in data, in the cosmological model, sorry, I would have something predicted like this. So the acoustic peaks would be something like this. And the data in this, say, rough prediction, much worse than Planck, do not go through the prediction. And the same is true on the other side. So this is the power spectrum P now multiplied by K cube, but just because in this paper they decided to do so. So these are the data, which are just these ones multiplied by P cube by K cube. And if you have no dark matter in your cosmological model, then you get something that does not go through the data. Okay. So I know that this is not satisfying in the sense that you would like me to produce this curve here with and without dark matter. I cannot do that in 10 minutes here. People do that. If you want to go in that review I mentioned, there are about 10 pages in which you derive this curve or this curve with and without dark matter. The basic point is that you need dark matter to reproduce the data. In particular, for the CMB, you need dark matter to reproduce a third peak here. Sorry, let me go back to this. You see that the third peak here is quite pronounced, and it's the same height of the second peak. This is the signature of dark matter. This is the imprint of dark matter. Without dark matter, this third peak would be lower, as you see here. And the same on the other side. You need dark matter in order to produce a power spectrum that goes through the data. If you have no dark matter, you will have something very weak, especially at large K, which means small distances. The physical, the verbal explanation of that is that you need dark matter to gravitationally catalyze the structural formations to produce structures which have a large K, which means a small distance. So you have to have dark matter to produce compact objects in the universe. Okay. Okay, so I know that's the least satisfying part, but believe me that this gives us evidence. People said at some point about 46 sigma for the presence of dark matter in the universe. Using this data here, I can fit the presence of dark matter or not in the universe with very high statistical significance taken at face value. Yeah. Which one? Okay, so this is the power spectrum. In this plot here, the vertical axis is the power spectrum, which is essentially the Fourier transform of the correlation function, which I try to explain here. I mean, it can be precisely defined, but that is what it means. And here I just took the power spectrum P and I multiplied by k cube, where k is the horizontal axis here. Just for ease of illustration, actually, it's not me that did it, but this paper here presents it in terms of multiplying by k cube. It's just the same plot, just multiply by k cube, so the data go up. Nothing special. I could have plotted actually this. The black line would do something like this here. Okay, yeah.
I was wondering, you always talk about dark matter, no dark matter, but there's like other fields like the modified quantum dynamics field.
Right, right. So this is exactly what is in the next slide.
Sorry.
Yeah. Okay, so I'm just going to touch on that. We could discuss again for an hour. So why am I insisting that I need to add dark matter and to add an extra substance and so on? After all, I always said that according to Newton's law, according to general relativity, according to gravity and so on, I need extra matter in order to explain the phenomenon. The other option is to modify the laws of gravity. Right? So this is another obvious option, which in what is, for instance, called the MOND, so modified Newtonian dynamics, or TeVes, which is the relativistic version of MOND, tensor vector scalar field of gravity, which has been proposed here. MOND dates back from the 80s, and TeVes has been proposed in the late 90s, and it's a sort of upgrade of MOND in the relativistic systems. So let me discuss briefly MOND, very naively, and then tell you that essentially it doesn't work so far. So MOND starts from this postulate. Instead of taking the Newton law, F equal ma, I modify it with a factor that is called mu of a. So a correction factor, function of the acceleration, which takes this form. Mu of a is equal to 1, so essentially no correction, for large accelerations, situations in which acceleration is large. And it takes the value a divided by the constant a0 in the case in which the acceleration is close to a small amount, given here 1.2 10 to the minus 10 meter per second squared. So in conditions of large accelerations, like the center of the galaxy, for instance, then no correction. In conditions of small accelerations, then a correction that goes as a. So let me stress that this has no, it's completely empirical. So it has no fundamental origin. There is no Lagrangian, there is no minimal action principle behind all this. Just I take Newton's law and I correct it by a correcting factor in your ways. Now, it's pretty obvious to see that if you do that, so the force balance between this new F equal ma here and Newton law here gives me that the acceleration is given by this formula here. Just turning around this equation. And since the acceleration is v squared divided by r, the tangential acceleration I'm talking about the rotational galaxies. Talking about the rotational galaxy. What I get is that v is equal to constants. You see, I turn this around, r simplifies, so what I have is that v is equal to constants. So this empirical modification included by MOND allows me to have a velocity of stars in rotating galaxies, which is constant as a function of r, flat, like we said before. So this fits the rotational curves of different galaxies very well. In different galaxies, you get that with just one parameter, which is this one here, you get something that fits very well most of the, actually almost all of the rotational curves that we see. And answering some other questions, so these are just 20 possible rotational curves, so there are many more, hundreds more. So this is intriguing indeed. So people could think that just modifying the Newtonian gravity or general relativity, one could explain the phenomena related to dark matter. Now the trick comes from the bad point comes from the fact that, okay, so rotation curves, yes, they work. But the other things that I discussed, no. or at least not as far as we know so far. So for instance, the bullet cluster, you cannot fit it unless you add some extra ingredients such as a 2eV mixed neutrino, which is now excluded by cosmology. This was proposed in 2006, but now it's completely excluded by cosmology. And it's quite obvious because in the bullet cluster and the other classes, what you're seeing is the presence of matter somewhere where, the presence of lensing where there is no matter, other than just those galaxies. So just modifying the laws of gravity, you cannot produce something where there is no matter. You see? So it typically doesn't work for weak lensing, and also it doesn't work for precision cosmology. So maybe you can try to make it in some way for the power spectrum. Okay, so what are we looking at here? Exactly the same plots as before, with the standard lambda gold CDM dark matter. So the standard model of cosmology including dark matter, and this new modified gravity theory called Teres. Let's look at the CMB plot. If you have the dark matter, then it fits the data. It's the dotted line, as we said before. If you do Teres, then you get something that doesn't fit the third peak. Okay? And that's because indeed, as I was saying before, you need dark matter to produce a third peak and also the rest of the hierarchy of peaks here. Why? Go and look at the text, but it's typical that you don't get enough power there. So let me just conclude with a comment before. So let's say we can close this detour saying that yes, it's possible that the actual solution of everything I said is modified gravity, but so far most people do believe in the community that adding dark matter is the right possibility. I should also mention that there is a recent paper by this guy, Kostas Kortis, and someone else a couple of years ago, where they claim that they have constructed a modified version of Teres with even more ingredients that can actually fit both here and here quite well. So maybe we're going to get close to something that works. So let's keep the door open. I should also say that this theory that they have is incredibly complicated. So it's like 3 pages of Lagrangian just to write down the details. So I haven't understood it. It looks very complex, but maybe it's the right direction. I'm wondering whether I should make a pause or not, or just go straight.
So we were considering to go on. Maybe we can stop for a few questions.
Yeah. So since now I'm switching the topic, if I'm done with the evidences, and I'll go back to the summary. Say, any questions on that, or I just move on?
Seems we can proceed, yes.
Okay, so let's go back to this list. This is what we learned, and we have discussed essentially this part here, but we have given some hints also on the other points there. Now let's notice one thing which allows me to move to the next topic. Something that I have not given any hint of. So cosmology doesn't tell me anything about the mass and the interactions of dark matter. Right? So, well, interactions, yes, a little bit, in the sense that in a negative sense. So cosmology tells us that this particle, this body, whatever it is, has to have very feeble interactions. But other than that, we don't know whether it's zero, as we said, then gravity, or something else very feeble. On the mass, really, we have no indications, right? So nothing here points to the mass of the dark matter particle. Not even this one here, as I said, it can be heavy or light, but because it depends on the corresponding momentum. So let's use the mass as a sort of organizing principle to discuss the possible range and the possible candidates that can be proposed, that have been proposed by particle physics and by astrophysics. So the range of masses that can be covered by dark matter is essentially given here. And it covers about 90 orders of magnitude. So it goes from 10 to the minus 21 electron volt to even some solar masses, 100 solar masses or so. I don't know if you realize how huge it's 90 orders of magnitude. It's incredibly wide. So the basic principle that if you have to take away one message from today, from this morning, is that dark matter can be made by a huge number of very light particles, again, corpuscles, or a very tiny number of very heavy corpuscles, as long as it has the properties that I discussed before. It's neutral, cold, stable, and feebly interacting. Okay. And this is really very huge. So just to give you an idea, if dark matter is made of something we discuss later, which are primordial black holes with a mass of, say, a couple of solar masses, it means that there is one particle of dark matter in the whole volume of the solar system up to Neptune. So you take a sphere that covers up to Neptune, and you have essentially one primordial black hole that corresponds to the total dark matter included in that volume. We discuss later the numbers, but this is roughly given. If dark matter is made of ultralight scalars, as called axions or axion-like particles, with a mass of 10 to the minus 21 electron volts, it means that in a volume such as my thumb here, there are about 10 to the 12 particles in each second passing by. Okay? In each instant, there are 10 to 12 particles passing by. So you see, this is the 90 orders of magnitude. One particle in the whole solar system, or 10 to the 12 particles in a centimeter cube. So it's very huge, and it's possibly the widest range ever thought of for physics search. So good luck to our friends with that. Okay, so the basic idea is that I will discuss different candidates by keeping in mind that each candidate I get should be neutral, cold, stable, and feebly interacting. We will see how it comes out from different theories later today. Before I move to that, let me give you a sense of all this range here. So where do the different benchmarks come from? So starting from the highest possible, largest possible mass. So we say that the largest possible mass, the heavier possible mass for a dark matter body particle is roughly, say, 10 to the 4 solar masses, which is the end of this range here, because that is the size of a dwarf galaxy. So if you take a dwarf galaxy, typically it weighs like 10 to the 5 solar masses, and the smallest one maybe 10 to the 6. And we see that it's inhabited by dark matter, meaning that the rotation curves is flat and so on. And so it has to contain at least 10, 100 bodies of dark matter, particles of dark matter. So this is the very, say, most extreme bound that we can have. The particle of the mass of the dark matter particle had to be smaller than a fraction of the mass of the dwarf galaxy. So 10 to the 4 solar masses, roughly speaking. Yeah.
How does this work out with rotation curves? Because I think the typical students' exercise is to derive isothermal halo distribution. That's basically a sphere which goes with R over -2. There's only one PDH.
No, indeed.
How does this work out?
It doesn't work. If it's only one, it doesn't work. That's why I'm saying that roughly, if the mass of the dwarf galaxy is 10 to the 5, 10 to the 6 solar masses, I want at least, say, tens or hundreds of bodies. In which case, you can. Yeah, I mean, this is really the maximum bound. You are pushing it to the maximum. It cannot really be higher than that, larger than that. But I agree that if you go into the very extreme, then you have too much granularity, say, so that would not work. By the way, what you're saying is exactly the 1 over R squared that was mentioned at some point. So is the thermal halo is the 1 over R squared that was mentioned earlier. And we'll see that it does fit even if there are better profiles. Okay, so this is to say that this is really, if you want to push it, the upper bound. We will see later that actually even for primordial black holes, this region here is not favored. We are rather in this window here, so we're not going to push too much the mass of dark matter. The other end, so the light, the very light particles. So if the dark matter is made of ultralight scalar fields with a mass of 10 to the minus 21, the bound is given by the fact that dark matter must be contained in the size of the galaxy. So here it's a matter of mass, and here it's a matter of size of the galaxy, meaning the following. So I always take a dwarf galaxy, because that's the smallest system inhabited by dark matter. I write down the de Broglie wavelength of a particle of dark matter with this mass here. So it's 2 pi. mv, the speed which the particle has in the dwarf galaxy. And it turns out that this is of the order of 1 kiloparsec. So this de Broglie wavelength has to be smaller than 1 kiloparsec, which is a typical size, rough size of a dwarf galaxy. So in other words, for a dark matter particle to be contained within 1 kiloparsec and not to have a spread of its de Broglie wavelength outside of the galaxy itself, it has to be that its de Broglie wavelength is smaller than about 1 kiloparsec. And if you plug in the typical numbers here with the speed of 10 to about 10 kilometers per second, which is typical of the dwarf galaxy, you get that the corresponding mass is 10 to the minus 21. In another way, if the mass is smaller than that, then the de Broglie wavelength is larger than 1 kiloparsec, and so you should have it basically spreads out of the dwarf galaxy, which is not consistent with what we see. The dark matter is contained within the dwarf galaxy. Okay? So that gives you the two ranges, and notice that they are based on systems which are dwarf galaxies, which are pretty solid. We observe tens or hundreds of them. And they can be, they are measured to contain a lot of dark matter and are also particularly clean as objects because being dwarf, they contain fewer stars, and so we can see their content a bit more easily. They have light mass over light ratio, a high mass over light ratio. So next, you see that here I have a sort of a benchmark that divides the area of particle physics objects and macroscopic objects. So around the Planck scale, 10 to the 19 GeV, we should say that dark matter, whatever it is, it's most likely constituted of an elementary particle. And if it's higher than that, if it's heavier than that, it's most likely constituted by a composite particle. Why? Because this is the Planck scale is the limit at which an elementary particle with this mass collapses into its own black hole. Okay, so an elementary particle can be heavier than this because of physics. So if dark matter is heavier than that, it's most likely a composite particle, such as an astrophysical body or a macroscopic dark matter, different possible candidates. It's not a sharp definition. I'm saying most likely an elementary particle here, most likely a composite object of some sort there. But you can consider composite dark matter also a smaller mass, but not the other way. Another benchmark is here. So you see that here I'm talking about fields, and here I'm talking about particles around a fraction of 1 electron volt. So 10 to the minus 1 electron volt. Again, this is not a well-established frontier. I'm just saying that if let's say the correct definition in terms of physics, it's always a field. Right? So quantum field theory describes fields and particles, depending on it's the fundamental of our understanding of nature right now. However, if the particle is lighter than this say psychological threshold of about 0.1 electron volt, you better describe it as a classical field. Like when you have a lot of photons, of low energy photons, it's better to describe them as a field. Collection of photons is better described as a field. And if instead it's a particle, then it's better described by if it's heavier than that, it's better described by a particle, and so you have something which is corpuscular in nature. Again, I'm stressing that it's not a conceptual difference, it's a quantum field theory all around, but it's conceptually easier to consider fields here and particles there. And finally, the other benchmark that I have is around here, so around a fraction of keV, electron volt. where I have that particles on the right can be bosonic or fermionic, and particles or objects on the left would necessarily have to be bosons, necessarily bosonic. How do I see that? Well, I can define an occupational number, which is defined as the density of dark matter divided by the density associated to each particle of dark matter. So I take the mass of the dark matter divided by the self-volume of the mass of the particle of dark matter, which is the Broglie wavelength cube. Okay, so you see here. So the occupation number is essentially intuitively how many particles of dark matter I can fit to reproduce the local density rho of dark matter. So these numbers we will see later. Rho is something of the order of a fraction of a GeV per centimeter cube. And if I plug in the numbers here, I find that if the mass of dark matter is smaller than this, then the occupation number is large. So in the individual volume, I have to fit many particles. That means that they have to be bosonic. Otherwise, by Pauli principles, they repel each other, okay? They exclude each other. If instead the mass of dark matter is larger than this value here, then this occupation number is of order 1 or less, and so that's fine. I can have either bosons or fermions. So when we discuss, for instance, later scalar sterile fields, if it's lighter than that, it will be necessarily scalars, such as axions or axion-like particles. If it's heavier than that, for instance, sterile neutrinos, they can be fermions or scalars. Okay, so the plan for the next bit less than half an hour is to go through this range here, jumping up and down, and overviewing the different candidates. Again, I'm not going into the details of each one, but the idea is to overview all of them, starting from some point in the graph and going up and down. Well, before I do that, any questions on the general principles? Okay, maybe later if you want. So we have to cover 90 orders of magnitude. It's a huge range. But there are places in that range which are more, say, popular for some reason. So we start around here. So around the weak scale. So around 100 GeV or 1 GeV, right? Which is the scale of weak interactions, which is what I call the weak scale, or the Fermi scale. Corresponds to the mass of the Z boson, corresponds to the Ragnar expectation value of the Higgs, and so on. So about, say, 1 TeV. These particles are particularly interesting because they are this class of particles, here, because they are the sort of paradigm of what we call the thermally produced dark matter. So dark matter which is produced thermally in the thermal bath of the early universe, and then have been left over. So what I'm going to discuss next in cartoons and with some equations is the so-called freeze-out mechanism, or the way in which one produces dark matter as a thermal relic from the early universe. Okay. So let's look at the plot first. In the plot, I'm plotting the density of dark matter particles here. Let's call it chi. Density of dark matter particles as a function of time. So time evolves in this way, or if you want, the temperature goes up, goes down in this way. So 1 over temperature or time, this quantity x. So essentially, here is the very early universe, say just after the Big Bang, so to speak, and here is today, when time is very high and the temperature is very low. So before I move on, another point is that this quantity I'm plotting here is the co-moving number density. So it's the number density of chi particles, how many particles per unit volume. in which I have subtracted the expansion of the universe. So I have factored in the expansion of the universe. Okay, so this is the definition of co-moving number density. Is the number density per expanding unit volume of the universe. Okay, so it means that when the particles are in a certain unit volume, if they don't go in and out of this volume because of different processes, then if the volume expands and they stay within, their density will remain constant. Their co-moving density will remain constant. I hope this is clear. So number density in which I factor in the expansion of the universe. Okay, so in the very early universe, I have processes in which I have, so the idea is that the temperature of the SoUP of the universe is very high, so I have a lot of energy around, and so I can produce and destroy at the same time particles chi. So remember, we're talking about particles with a mass of around 100 GeV or 100 GeV or 1 GeV. The energy is much larger than that in the early universe. And so what you have is that two dark matter particles can annihilate into final state, imagine for instance electrons and positrons. But at the same time, the electrons and positrons in the bath can produce particles chi because there is enough energy in the bath. So annihilation and reproduction of dark matter particles. So in some units, this co-moving number density is, say, at equilibrium in the sense that you have the same amount of particles in the standard model and in terms of dark matter. Created and destroyed continuously. Then, as the universe expands and cools down, the energy at disposal in the thermal bath starts decreasing, right? So you have annihilations that continue, so you can destroy particle and antiparticle dark matter going into electrons and positrons, but you don't have enough energy to reproduce them from the thermal bath. The electrons and positrons now have an energy below the mass of the particle, and so typically you don't reproduce them. So what happens is that the co-moving number density of particles decreases because you destroy them without reproducing them. So it goes down following the Boltzmann suppression related to the mass of the dark matter particles. So this is the exponential going down with at the exponent the mass of dark matter divided by the temperature. Actually, temperature divided by the mass of dark matter. Naively, this means that you destroy them because you cannot reproduce them, so little by little you deplete the density of dark matter particles. As the universe expands even further, what you find is that at some point, even the annihilations stop, freeze. That's because if the dilution due to the expansion, if the dilution due to the expansion proceeds at a given level, that at some point, even two dark matter particles cannot find each other anymore and annihilate. Okay? The rate of annihilation freezes, stops, the annihilation stops because they don't find each other given that they have diluted so much as time goes by. So what happens is that their co-moving density freezes, stops. And so what you have is that this goes to a plateau and to a constant. So the amount of particles left over by this incomplete annihilation process is the amount of particles that we have today. Is the amount that we have today, which is the result of a frozen annihilation process. So it's a thermal relic, it's a relic, something left over from this annihilation. This moment in time is called the moment of freeze out. So the moment in which the annihilations stop following the decrease and everything stops and freezes. Okay, so notice that this is, as is marked here, inversely proportional to a quantity which I call the annihilation cross-section, sigma A, multiplied by the speed and averaged. But the important thing for me is to focus on the sigma A, so the the annihilation cross-section. And this is a sort of intuitive. So if the annihilation cross-section, so the probability that two dark matter particles annihilate, or actually the dark matter and anti-dark matter annihilate, if the annihilation cross-section is larger, then it means that the annihilations will proceed for longer, and so fewer particles, which freeze out will happen later, and so fewer particles will be left today.
I have a question.
Yeah.
You say they are not annihilating because they are not finding each other.
Yes.
So maybe spots will have more matter than antimatter.
Say it again. I know. Okay, so this is okay. So an implicit assumption here, which I didn't even mention, is that we are in a symmetric condition. So dark matter and anti-dark matter have the same amount. Later, today or tomorrow, I don't know, we discuss a mechanism in which instead you have an asymmetry between matter and antimatter, and dark matter and anti-dark matter, but that's a completely different mechanism. Here I'm discussing the case in which it's symmetric in the dark matter side. That was a question or not?
Yes.
Yeah. Okay, so implicitly I'm assuming total symmetry. Okay? Dark matter and anti-dark matter are equally abundant, so they don't find each other simply because they have diluted so much that they don't find each other. That's the mechanism. So I was saying, and instead, if the annihilation cross-section sigma A is smaller, then the annihilations will stop earlier. The strength of annihilation is relatively smaller. And so the frozen out density will be larger, right? So it means that the quantity that we get today is inversely proportional to the annihilation cross-section sigma A, or more precisely to this quantity, which is sigma A multiplied by the speed of particles in the thermal bath averaged. But this is sort of technical point. The important quantity is sigma A. Okay, so this is the cartoon, right? Gives you all the ingredients, but there are equations behind it. So again, I don't have the time to go into the equations, I just give you the final result. If you solve the Boltzmann equation in the early universe, Boltzmann equation means that the evolution equation of this quantity, the number density of particles chi, as a function of time, just means that. Boltzmann equation is the evolution of number density as a function of time. So essentially, is the equation that gives you this result here. Solving the Boltzmann equation in the early universe gives you the result that omega x, omega, is a number divided by sigma annihilation times V, so this quantity here, averaged. Constants, so there are many constants here if you want, but they boil down to a certain number divided by the annihilation cross-section. So you see that the units are correct because I'm talking about an annihilation cross-section, so a surface, so centimeter squared, times V, so centimeter per second, and so this number here is the same as units on the number denominator. So if I said that the rate cross-section, so first you notice that indeed, as I was saying, that omega, the final omega is inversely proportional to sigma V, as plotted here. And next, let's notice one thing. If I want to reproduce omega dark matter in the correct amount, so 0.26, so 26%, then it means that I have to have an annihilation cross-section times V, which is 3 × 10⁻26 centimeter cube per second. If I plug this number in here, I get roughly 0.1 or 0.2. Okay? So cosmology is telling me that if I want a particle to be produced in the right amount, it has to have an annihilation cross-section of this order here, 3 × 10⁻26 centimeter cube per second. This is what is called the thermal annihilation cross-section, or the cosmological cross-section. If a particle has this cross-section here, it's automatically produced in some sense in cosmology in the right amount by the mechanism that I just gave you here. It stops, it freezes out at right moment to produce this number here. Okay? Okay, So let's have a look now at particles with weak interactions. So particles with interactions mediated by SU2 left of the standard model. The weak interactions that we call weak in the standard model. So I can estimate the sigma v for that particle. It will have alpha weak divided by the mass of the mediator, or the mass of the scale in plane. So alpha weak is equivalent of the electric charge, but just for the weak interaction. So it's written here. It's basically G weak divided by 4 pi. And this typical scale is, as we said, 1 TeV or 100 GeV, which is the mass of the mediator of the weak interactions or the mass of the dark matter. The two things mix up. So this is the typical estimate done by hands of the annihilation cross-section of a particle which has a SU2 left weak interactions with the standard model. And what it comes out? It comes out that this quantity here is precisely giving this number here. So weak interacting massive particles, WIMPs, have naturally the annihilation cross-section which corresponds to this, to the magical cosmological cross-section. And so the omega x that comes out is exactly the number that you need in cosmology. So these are two completely different things, right? On one side, I have the number required by cosmology that gives me the correct rate of abundance. And on the other side, I have the cross-section predicted up here, given or taken order of magnitude, predicted by particles that have interactions mediated by the Z and the W. And the two numbers happen to be the same. This is what is called the WIMP miracle, some people call it. So the fact that WIMPs miraculously turn out to have the right amount of cosmology. Again, you realize that the two things are completely disconnected. Weak interactions work, but the cosmological required perception in principle has nothing to do with them. Okay. Is it clear enough? Yes. So the idea is that WIMPs are very popular, weakly interacting massive particles, so particles with weak interactions in the sense of SU2 of the standard model, so mediated roughly by the Z and the W, and with a mass of the order of 1 TeV, which is the mass of the weak interactions, WIMPs, are popular because they are automatically producing the right amount of cosmology. And this is why so many people are looking for WIMPs still. Okay, so we have discussed how WIMPs are produced in cosmology and how thermal particles, thermal dark matter more in general works. So around here, as I said, in the early universe, you have a thermal bath, and then the right amount of dark matter comes out from the mechanism we just discussed. Now the question is, are there any theories from particle physics that produce a particle around here, around the weak scale? So a particle with weak interactions and a mass of the order of a few hundred GeV. The question is, yes, there are many of these theories, and to be historically say accurate, I would say that the most popular candidate of all in the past 50 years or so is the neutralino motivated by supersymmetry. So this candidate has been dominating the field in the last 50 years. And say, if I had given these lectures about 10 years ago, I would have said, okay, so dark matter is the supersymmetric neutralino, and a few other possibilities or exotic possibilities are possible. Only crackpots work on that. SUSY neutralino is the answer. Next, I mean, in the last 10 or 15 years, the panorama has changed completely, and we will see that. But I think it's fair to explain how the neutralino comes out from supersymmetry, and so let's spend 2 minutes on that. Who has already heard about supersymmetry and neutralinos? half of the audience, or maybe 1/3. Okay, so I will I have like 10 minutes left, so I will discuss very, very naively, phenomenologically, supersymmetry, in particular how supersymmetric dark matter comes out in 2 minutes. Maybe it will be 10, but let's say I will be precise. And it will be really phenomenological. Right? So supersymmetry is a huge theory with a lot of mathematical implications. I'm not going into that. I'm just saying very down to earth and focus on that. So the basic principle is the following. You have a standard model here with the quarks, the leptons, the force carriers, and the Higgs boson. And we know that the Higgs boson has a mass, which is measured by the LHC of 125 GeV, quite precisely. Okay, so this is a measured mass. The standard model does not predict the mass of the Higgs boson, as you know. Now, it's even worse than that, in the sense that if I take my theory, so the standard model, as a quantum field theory, and compute the first order corrections to this value here, I get a very large value. So if I compute the one loop or the first order corrections to the mass of the Higgs, I have the diagrams of this sort, where I have a loop of, say, another particle, such as the top quark, enters, and this gives me a correction to the mass of the Higgs, so a delta, or first order correction to the mass of the Higgs, which is of the order of 10 to the 19 GeV. So what I'm saying is that the first order correction to this value here, given my theory, is 17 orders of magnitude larger than the measured value, which is a huge disaster. It's a failure, in some sense, of the theory. It tells me that the first order correction is 17 orders of magnitude larger than the zero order number. Clearly, something is not going right. So this is the so-called hierarchy problem. So the question of why the first order correction is much larger than the measured value. Or seen in another way, it's the question of why. Well, first let me tell you where this number comes from, roughly speaking. So the idea is that the Higgs boson, as it propagates, can sort of create loops of particles, such as in particular the top quark. And I'm focusing on the top because it's the most important one, in the sense that it's the one that contributes the most to this loop here. And this loop here, I have to circulate the top quark with momentum as high as, I have to integrate overall the momenta up to the maximum scale I can think of. The maximum scale I can think of is the Planck scale, because that's where my, say, theory blows up. And so this correction will be proportional to the Planck scale, which is the maximum momentum I can put in here. So this corresponds to the Planck scale. So I'm saying that the correction at first order is dominated by the Planck scale, while the mass of the Higgs boson is close to the Fermi scale, the hundreds of GeV. So the hierarchy problem is expressed another way, is asking why the Planck scale is so much larger than the weak scale. 17 orders of magnitude. Or, yet another way, why gravity, which is connected to the Planck scale, and so G Newton contains the Planck scale at the denominator, is so much weaker than the other forces of the standard model, in particular the weak interactions, which are related to the mass here. G Fermi contains the mass of the W at the denominator. Okay, so the hierarchy problem is a problem that we have intrinsically in the standard model alone, which can be expressed in the way of saying the corrections to the Higgs of the mass are 17 orders of magnitude larger than the measured value. So my theory is inconsistent in some way, psychologically inconsistent, philosophically inconsistent. Okay. All this has been debated by decades, and I'm oversimplifying with a little plot, but I mean the principle is more or less correct. So one of the solutions to this problem is the following, is to postulate the existence of another sector of particles, so doubling the particles in nature, including this new sector that we call the supersymmetric sector. So we take the particles of the standard model and we double them, we create a sort of partners, supersymmetric partners, is called, of the particles of the standard model, which I denote here with the same symbols, but just with a tilde on top. So as we have the electron, we have the super electron, which is this one here with the tilde. As we have the top quark, we have this top as the super top quark, which I call the T with the tilde here. And then for technical reasons, the Higgs has to be doubled, and you have two Higgs partners indicated by H1 and H2 tilde there. So these particles have the same properties as these ones. So for instance, the charge of the super electron or electron is the same as the charge of the electron. And at this stage, they have the same mass as the particles of the standard model. But for one property, which is the spin. So the particles which are fermions here have a partner, which is a boson. So the electron is a fermion, the super electron, this electron is a boson, is a scalar. Or the photon is a boson, it's a vector. The super photon, which is called photino, is a fermion. Okay, so apart from this, the two partners, the two sectors are equivalent. Now the trick is that if these particles exist, they also contribute to the loops of the Higgs boson. And in particular, also the stop quark will contribute a loop like this. Now, since the stop is now a scalar, the graph is roughly is different. And if you do the computation, it turns out that the correction to the mass of the Higgs is equal to the one before, but with an opposite sign. Just because this is the fermion, this is the boson. So, roughly speaking, you understand that this cancels this, and we are safe. So that's why this number is small, just because this correction goes away. Okay. So supersymmetry solves the hierarchy problem simply by introducing a set of particles that cancel the embarrassing first order correction of the standard particles. Now, of course, the supersymmetric sector cannot exist in the way it is, because otherwise we would have seen a Higgs electron with the same mass of the electron or with other particles. So what happens is that the supersymmetry must be broken, so there must be a gap between the particles of the supersymmetric sector and the particles of the standard model sector. And the basic assumption, say, up to 10, 15 minutes ago was, okay, so this gap is of the order of, say, 200 GeV. And this explains why the cancellation is not perfect, and you get something which is of the order of mass of Higgs. Okay. So this is a way to solve the hierarchy problem. But where is dark matter? So why do I talk about this? Well, there is an extra step which we have to take, which is to say that we impose the existence of a new quantum number that we call the R parity. Actually, we don't impose it; it comes out from asking some property, but for our purposes, it's just a new quantum number that we put on top of this. And this new quantum number is R, that is equal to +1 for the particles of the standard model, and -1 for the particles of the supersymmetric sector. So I impose that this number is +1 for the standard model sector and -1 for the supersymmetric sector. And then I impose also that this quantity is conserved. This new quantum number is conserved, like electric charge is conserved, say. Okay, so let's look at the particles on this side. They will have different masses, typically large masses, with a sort of spectrum. There will be lighter particles and then heavier particles in the supersymmetric side. So the heavier particles in the supersymmetric side will decay into the lighter particles in the supersymmetric side, plus a combination of possibly these particles here, always respecting the r equal to -1. So if you have a particle here with r equal to -1, it will decay into another particle, so r equal to -1 is conserved, and the combination of these, such as the things cancel. But when I get to the lightest particle of the supersymmetric sector, the lightest particle cannot decay anymore, because it should decay into standard model particles, which are lighter than she is, but it cannot, because it would violate the conservation of r equal to -1. You cannot decay a particle of r equal to -1 into any combination of r equal to +1 particles. Okay. So the lightest of the supersymmetric particles is stable, because you have to conserve this equal to -1. I think you see where I'm going. So if I consider the neutral particles of this side here, for instance, the photino, the xeno, and the two Higgs xenos, these are particles that are electrically neutral, because these are the partners of these particles which are neutrons, electrically neutral, charge equal to 0. These are stable because of the phenomenon that they just gave. You want to conserve R-1, so you cannot decay. These are feebly interacting. Well, okay, they are precisely the interactions of the, they correspond to the interactions, the feeble interaction of the standard model. And they are cold because they are heavy because of this gap here. So these particles here are good matter candidates in our criterion that we used earlier. Right? These are the neutralinos. So these four particles here are collectively called the neutralinos. They are the partners of the neutral particles of the standard model, and are good dark matter candidates, precisely as I said a moment ago. If you want to focus on one, say, say that they will redistribute, so they will have superpositions among them, and you can think that one of them will be really the lightest, and the other ones will be slightly heavier. So the typical good dark matter candidate is the lightest of the four neutralinos, combination of the four neutralinos. Now, before moving on, let me tell you that this. So why this picture is a bit in trouble? Well, for different reasons, but essentially because we turned on the LHC in 2009, and the LHC has not discovered any supersymmetric particle so far. So this gap here is now 2 TeV or more. So the energy of the LHC has allowed to say that if supersymmetric particles exist, roughly speaking, they have to be heavier than 2 TeV. So you understand that we are back at the initial problem. So we have again a hierarchy problem now between this gap, which is big, and this value, which is small. Okay, it's a small hierarchy problem, as people call it, a little hierarchy problem, but it's still an embarrassment, a little bit of an embarrassment. Okay. So the fact that the Higgs, the LHC has not found yet supersymmetric particles sort of makes it less fashionable to think of their quantum in terms of supersymmetric neutralinos. They are still possible, but less hidden in some corner of the parameter space. So I will leave you with this picture. The idea is that the supersymmetric neutralino has become one of many candidates in the past, say, 15 years, and many others have become popular or have come back to popularity in the last few years. For instance, Kaluza-Klein dark matter, which is dark matter that comes from extra dimensions of space, or axions, and we'll have a full lecture on this later in the week, or minimal dark matter, which is the best model of all because it's my model, or others, like little Higgs dark matter, Cirelli neutrinos, baryons, and so on and so forth. So this is a collection of crazy names that I have fun collecting. You see, so some of these are my photos, so this is my model for and I'm not. Okay, so these are a selection of the possible models. We are done, but just to finish, this is a selection of the possible models that have been put out on the literature in the last 10 years or so. I just selected the most, the craziest ones in terms of names. But the important thing to keep in mind is that each one of these is a serious model, apart from the name, maybe. So behind there is a candidate which is stable, electrically neutral, cold, and fluid interacting. So I can pick any one of these and tell you, okay, so in this model here, there is a candidate which has these properties, and so it can be a good term. With a range that varies by orders of magnitude, of course. So the plan tomorrow is to take another example of these, scalar singlet dark matter, which is hidden somewhere here, and then move on to other possibilities. Explore like 4 or 5 of these possibilities. Okay, done.
I think we have a few minutes for some more questions, if any.
Yeah.
So just on that last bit, when the gap was 200 GeV, but now they're saying because they haven't found it in the colliders, it's got to be more than 2 GeV.
Yeah.
What's the limit of the collider? What's the limit of CERN again? Like how far can they look?
Okay, so the LHC has an energy per beam which is 7 TeV, right? So in the center of mass energy you have a 14 TeV. But when you collide protons with an energy of 14 TeV, you are actually colliding quarks and gluons, which are the partons contained inside the proton. And so those partons carry a fraction of the energy of the proton. So even if you collide 14 TeV in the center of mass, basically the partonic collision, which is the microscopic process, is, roughly speaking, a collision between 2 quarks, which carry each one a fraction of that momentum. So roughly speaking, you can think that each quark carries a third of the energy or the momentum of the proton. So a couple of TeV, or even less. And so that's why this is the basic the sort of benchmark. You are colliding the center of mass a fraction of so up to a couple of TeV at most. That's why the benchmark is there.
So what's next for supersymmetry theory? I mean, what are they going to be able to do to confirm it, or are, for example, if we find a WIMP, would that confirm SoUP?
No.
Can they confirm it in a way?
No. Okay, so WIMPs is more general than supersymmetry, right? So as I said before, WIMPs are in general particles that interact weakly. They are not necessarily neutralinos. The neutralino is an example of a bigger class, which are WIMPs, right? The class of WIMPs is defined by the fact that they interact weakly and have a mass of the order of 100 GeV. The neutralinos happen to have those 2 properties, but they are just one example of possible WIMPs. So if you find a WIMP in xenon, you don't confirm supersymmetry at all. It can be some other kind of WIMP. For instance, minimal dark matter is an example of WIMPs which are not supersymmetric. Next, what do we do? So supersymmetry can clearly exist at higher scales. So if supersymmetry exists at 10 to the 15 GeV, we'll never discover it at colliders, not even futuristic colliders, of course, but it might be an ingredient of string theory or something else. So supersymmetry is not dead at all. It's low energy supersymmetry, so supersymmetry predicting the low mass for these particles here, whereby low I mean a few TeV or like most, that it is in trouble. I'm not saying it's excluded. Maybe tomorroh the LHC in one of the corners of the parameter space which are still unexplored finds a squark or a lepton, and it will be a huge discovery. But it's true that grounds have been covered, and so far not great.
Thank you.
Sorry, does the argument of the miracle is already valid for GP or sub-GP WIMPs?
Tomorrow, we'll see tomorrow. There's something called the WIMP-less miracle. It's a translation of the WIMP miracle to the thing that you are mentioning. We'll discuss it tomorrow.
Okay, so I think we can thanks again. So a few intros before going to the coffee break. If about the poster session, please bring your poster to the secretaries if you have not done it yet. And today we have the speed talk, so same argument. You have to upload your 2 slides for today in the form that we sent around. If you didn't do it, please do it as soon as possible. Now the coffee break starts now. It's upstairs, and then there is a terrace. Weather is fine, so we can relax. We reconvene at a 11:15 with the lecture on neutrino phenomenology. Pardon me, yes, 11:15. You can leave everything here. It's we are running. Yeah.
Ottimo. Metto su internet, un PDF le metto su. Mi hai dato.
Era il tuo account, quindi dovresti essere le carichi su
PDF perché non ho filmati, non ho animazioni.
se preferisci fai col PDF, in quel modo le carichiamo già su sito.
Oppure fermarla, così tanto salva il file e poi le fai già ripartire. Poi casomai la faccia ripartire anche dopo, poi cancellerai il file con la pausa, se no è più comodo.
Poi comunque fare un giro di editing, la registrazione tagliando qualche parte punto morto.